Good morning, everybody. I'm Piera Patrizio, and I'm working on, together with Professor Niall McDowell, on work package 6 of the project. And the overall idea of our work is to try to understand what is actually, first of all, what are the implications for scaling up greenhouse gas removal technology and integrated in the energy system. And also, importantly, what are the necessary preconditions that we need to have in order to do GGR efficiently from, of course, in terms of the energy system requirements and also considering also local conditions. So I put up this slide talking about what actually is GGR, just to kind of like express the way we are, the angle in which we are kind of like thinking about GGR when we are modeling this technology and we are understanding their potential integration in the energy system. So what we want to do with GGR is that we want to remove carbon from the atmosphere in a way that, of course, is somehow permanent. Importantly, in order to achieve net removal of CO2, the upstream and the downstream emission that are associated with the capture, the remove of the atmosphere, and then the store of the CO2 in some form of storage need to be accounted for in the emission balance. And so in other way, or in other terms, basically the total quantity of atmospheric CO2 that is removed and permanently stored needs to be greater than the total quantity of CO2 that is emitted along the supply chain. So I'm sure you know, you're aware and familiar of this picture, and I'm actually glad that nobody has put it on. We know that there are a wide range of GGR options that are available. First of all, they differentiate depending on the way the CO2 is removed, but also we also have different implementation options within the same GGR pathways. Of course, also as well, we also have different type of storage. We have geological storage in which the CO2 is removed, transported, and then permanently stored underground, or we can have other type of store in biological formation. So it is clear already from this slide that there is a wide range of options available, and even within the same pathways, we can have a wide range of complexity that need to take into account, especially when we think that our overall goal is to try to efficiently removing CO2 from the atmosphere, and so accounting for all the different sources of CO2 emission along a GGR supply chain. So this is, for instance, the example of the way we're thinking about deforestation. So you see here that this curve represents the CO2 sequestration potential of trees. And you can see that, for instance, not only this CO2 sequestration potential, so the overall CDR efficiency, so the removal efficiency of this option, is not constant over time, but actually it started slowly, and then when a tree reaches maturity, you have kind of like a peak of sequestration potential, and then it can slow down depending on wildfire, for instance, or depending on the forest management practice. But also, most importantly, this CO2 sequestration potential depends on the location. So depending on the climate you're in, you can have a very high sequestration potential for afforestation projects that are grown in Brazil, for instance, in the tropical rainforest. And then on the lower hand, we see, for instance, the sequestration potential of planting trees in the UK in boreal conifer forests. The same can also be said about this complexity for BECCS, for instance. So BECCS, one of the reasons why BECCS pathways were quite popular and had been featured in all the IPCC reports and all the IAM model is also because besides removing carbon, it can also offer another form of service, which is heat, power, or transport fuel. However, depending, of course, on the type of pathways we are looking at, we can have a certain amount of CO2 that is actually definitely permanently removed. So on the left side of this figure, we have, for instance, the pathways that adopt BECCS for the production of electricity, which is quite efficient in terms of CO2 removed. And then if we move farther down to the left, we have almost very minimal CO2 that can be removed for a pathway of BECCS that, for instance, produce biofuel. At the same time, these figures also show how the overall contrafactual scenario that we're looking at is important, because, as I said before, BECCS produce also some sort of energy carrier, but depending on the energy or the carrier that we are substituting this bioenergy with, then we have a certain avoidance potential that needs to be taken into account. The other one that is quite interesting and quite challenging is direct air capture. So direct air capture, as I'm sure you all know, is a technology that removes CO2 directly from the air. It seems quite simple as a concept, but in reality, the main challenge of this technology is the fact that because CO2 is quite diluted in the air, then it requires a lot of energy. So here I presented the two concepts that are now being investigated for direct air capture, which we are thinking about within our modeling framework. This is the liquid solvent direct air capture and the solid solvent direct air capture. And although the overall technology is different, the core principle, the principle is overall very similar. And because they both rely on a lot of energy for their continuous operation, you can see here on the lower part of the screen that actually the carbon intensity of the electricity that has been used for making duct work, it's really important. So here you see the CO2 removal efficiency from red to blue, and depending on the location where you're at, you actually can even get negative CO2 removal efficiency, meaning that the process is actually consuming more energy and therefore is not really overall net negative. So the way we are thinking about in the project of integrating all of these range of pathways is by using the MONET Framework. The MONET Framework is a model, a linear model that has been developed throughout 5 years within the group. And it is considering a range of spatial inputs, such as, for instance, the electricity carbon footprint of a different location. It works for 5 regions at the moment, so it's Brazil, US, India, China, and Europe. And now recently has been upgraded by increasing the spatial resolution of the UK region, since the focus of the project is, of course, the UK, or most importantly, UK. So it considers a range of spatial inputs, such as, for instance, the climate as well, where that we're looking at, the CO2 storage availability, the water stress index to provide an indicator of the overall impact of using water for GGR. And then it has also a temporal resolution. It works from 2020 to 2100 with a 10-year time step. And it also considers some potential evolution of the energy system, which is one of the most important feature in the fact that it's assumed that the energy system can decarbonize. We can, for instance, increase the amount of biofuel being used throughout the time, and also the reduction in carbon intensity of electricity. The overall idea is to identify, the optimal portfolio of GGR technology that can be deployed to meet a certain target within a certain region, or identify what are the overall costs, environmental and social impact associated with deploying these technologies. And that's why the model can work with different objectives, either, for instance, minimizing the investment in these technologies, or the water use, or the biodiversity impacts, which is the recent development. So in terms of output that this framework can provide, here I've put up a result that has been published by Niall and Mathilde Vachardy, who was a PhD student in our group. In this study, they were looking on when actually BECCS can be consider it really carbon negative, because as we heard before, there are different impacts that need to be accounted for, and one of the most important for sure in the case of BECCS is the land use change. So basically, as you move, so these are all different scenarios of potential BECCS supply chain that have been investigated with the model. From top to top to down, you basically see different scenarios that consider, for instance, less carbon-intensive supply chain through the use, for instance, of biofuel, or the use of carbon-neutral electricity. And then within the same scenario, as you move with time, we are also assuming that there are some improvements within our supply chain as well. So the overall idea of this study was that, yes, BECCS can provide actually carbon-neutral electricity, but the condition matters. Another analysis that we are currently working on, because we are working on integrating biochar pathways within the model, is to try to understand actually how the overall carbon removal efficiency of biochar pathways change, depending on the location, on the feedstock that we are considering, and on, depending, of course, on the overall configuration of the supply chain of biochar. So here is presented the different option and the schematic representation of the steps that are involved in the production of biochar and its, of course, distribution in the fields. And you can see, for instance, from these two case studies that consider a supply chain using forestries or energy-dedicated crops that are being spread in the UK, how the overall removal efficiency of this technology changed dramatically from over 40% to around 16%. And this is because, of course, we need to account for land use change associated with growing this energy crop, but also with the overall CO2 emission that have been released in the supply chain, and also importantly on the permanence and of this type of pathway. So just to conclude, I've also wanted to highlight the fact that at the moment we are also not looking only at CO2, at carbon, but we are also trying to consider other environmental impacts, such as, for instance, the impact on biodiversity. The reason is, of course, that in order for the UK to meet the net zero targets, it is expected that, especially if we consider land-based GGR technology, we're going to rely more and more on biomass, and most probably also on biomass imports. So here, it's a case study that we're currently working on, in which we are considering the potential sources of biomass supplies. We have identified here the Southeast US and also the Atlantic coast of Brazil. And here are represented all the ecoregion and the potential biodiversity impact associated with using land for like forest, extensive forests for then producing forested residues used for BECCS, for instance. And so what we are trying to do now is to look at different objectives of meeting these UK targets with also accounting for biodiversity, which is represented by this green area that you see here on the left. And interesting, what we are seeing is that when actually we try to protect biodiversity and still trying to meet the target of the UK of removing 90 megatons of CO2 per year by 2050, we see that we have an increase in extensive forests, meaning that we are relying more on afforestation, which is better for biodiversity. And this results also in a reduction of biomass imports, and so on a reliance on domestic feedstocks, such as, for instance, also energy crops. An overall increase in the removal cost, but little. We are around $100 per ton of CO2 in terms of removal cost. And, of course, also potential benefit effect for biodiversity. So that's all from my side. Thank you.